We're going?
Yeah.
Fantastic. I'm Steve Rumble. I'm one of the grad students on the RAMCloud project. I'm going to be talking to you guys today about log structured memory in RAMCloud, which is a little bit of a misnomer because our storage is both in memory and on disk, and those two are kind of intricately tied together, so we'll kind of go back and forth. This is, unfortunately, the very first of these, hopefully, many recorded videos. I'm going to try to talk about both concepts and code so that you have an idea of what exists, why it exists, and more importantly, what the heck the actual implementation sort of looks like, so you can fish around inside the source code and hopefully hack on this. And I'm sure you'll find ways to improve upon this stuff and be eager to do so. I guess since this is the first time, we should probably start out with like a very rough overview of what RAMCloud is, or at least the major components that are kind of necessary for understanding this. So RAMCloud is just a storage system. This is RAMCloud. It's a storage system that stores basically key value pairs. So it's like a giant hash table distributed across many machines in a data center.
In case it wasn't all clear before, please interrupt with questions along the way. Don't try to save them for the end.
Yeah, so anybody listening to or watching the video can't actually hear anybody else in the audience, but John is encouraging people to ask questions, and if they can remind me to repeat the questions, that'll be a lot less confusing for viewers of this stuff. Right, so RAMCloud is basically a giant store for key value pairs, very simple data model, and it's a distributed system for data centers. And we like to claim that its kind of two main goals are large scale and low latency access. So we combine many machines together, kind of collect all their DRAM so we can store a lot of stuff in there. And by storing it all in DRAM, hopefully we can access it very, very quickly and shuffle it to clients across the network. Okay, then what does log structured memory really mean? What does it have to do with? So in RAMCloud, we end up having a whole bunch of servers in a cluster. I'll be drawing lots of boxes and arrows. We have various types of servers. So if this box is one type of server, we might have, and by server I mean more a process than a physical machine. We have machine or servers called masters, and these are basically what store all the data that we access. And masters basically consist of two relatively simple data structures. There are a few others, but for the purposes of this presentation, they're basically two that we really care about. There's a hash table, and then there is basically a giant chunk of DRAM that stores all of our objects. And for reasons that will hopefully become a little more clear later on, we actually structure our DRAM as a log. So basically, when we store objects, you can think of your DRAM as kind of this giant tape in a way, and every time we write an object, we just append it onto the end of the tape, and we go on and on and on. And then in order to be able to access these objects very quickly, we point to them from the hash table. So, you can service a request by taking a key, looking it up in the hash table, finding the object in DRAM, and sending it back to the client. And so we have many, many, many of these masters. And because we actually care a lot about the data that we're storing in the system, we have to ensure that it's durable, because if an object is just living in the memory of a machine, if that machine disappears, we've got a problem. If the power goes out, that's volatile, we also have a problem. So we have other servers in the cluster called backups. And basically what backups do is store pieces of our logs for other masters. So a backup is basically a little bit of a master's log in DRAM, and if I can draw a really awful hard disk here, something like that. Basically what happens is every time we write data to a master, we we replicate a little bit of that data to a backup somewhere in the cluster. We'll get into a little bit more detail about how exactly this works. And then eventually, that data gets flushed to disk so that it's persistent. Yeah?
Does the hash table also live in DRAM? Because your diagram seems to suggest that DRAM is separate.
Yeah.
Repeat the question.
Does the hash table live in DRAM? Because I've sort of drawn this as being all of DRAM, so this is maybe a better label for this is log or log DRAM. So the majority of the server's memory is structured as a log. A smaller chunk is chopped off and used to store the hash table. Yeah.
Is a smaller chunk chopped off statically? Like, do you know how big the hash table is going to be?
Question is the hash table statically sized? Right now it is, yes. That's just because that's how we did it initially because it was simple. Probably should be changed sometime in the future, but it hasn't been a problem so far. Basically, I think most of the time we assume we chop off probably more memory than we need for the hash table. It doesn't have very high occupation.
Quantitatively, how much?
It would.
Hash table, do you remember? How much memory do you chop off for the hash table?
We have, yeah, how much memory do we chop off for the hash table? Right now, I think it's 10% of whatever you give to RAMCloud. So where did that number come from? Completely out of the air. So yeah, hash table is extraordinarily simplistic. So you might be wondering right now, this seems a little bit weird. Why do you structure memory as a log? So if you're familiar with log structure file systems, kind of one of the big benefits of a log is that you can get very efficient disk I/O. So basically, this doesn't really answer the question of why the DRAM is structured as a log, but if we have the same structure in DRAM as on disk, that implies that we're structuring our disks as a log, which means that we can batch up lots and lots of writes together. We can issue large IOs to disks, and we can amortize seek and rotational latencies and get very high bandwidth out of that. And that's important for several reasons. For one, we want to support very small objects and get very high bandwidth with small objects. So if we buffer them all together, then and write them out in large IOs, then we can get high bandwidth, even though we have relatively small objects. We're not seeking all over the disk to write little tiny pieces. And it's not just writes that we care about reads too, because if one of these machines fails, then we've lost all the data in DRAM, and somewhere in the cluster there's a copy of its log. We want to be able to read that back out very, very quickly so that we can recover. We don't actually redundantly store data in DRAMs of multiple masters because we want to make efficient use of memory. Memory is pretty expensive, so we don't replicate in main memory. But we do replicate on backup disks, and maybe now is a reasonable time to explain how this is actually done. It's slightly more complicated. So a master's log isn't, you can notionally think of it as like one long contiguous tape, but it's not actually contiguous. So if this is, again, kind of the log, basically what happens in memory is we chop up the DRAM into a bunch of pieces we call segments, just like the LFS terminology. And then we write objects to individual segments. So let's say this is kind of an old segment. We filled it up with some objects. Hash table here for just have it complete. And basically what happens is we have segments for a few reasons. One, which I'll get into later, is that it makes actually defragmenting the log in the future more efficient. But another is so that we can actually spray the log across many backups. So what ends up happening is, as we fill in the log in memory, we replicate segments to various different backups in the server. So, we might have 10,000 servers. Each of those 10,000 servers might play both a backup and a master role. And what happens with masters is, as we start writing objects into segments in the log, we actually replicate those segments to other backups in the cluster. We usually choose 3. 3 seems to be a reasonable number to get us the kind of durability requirements that we want. And then eventually what happens is, so this is actually replicating segments to backups that are storing these buffered in memory. Eventually, we end up filling up these segments with new objects, and then we flush these to disk on the backups so that we're not actually using a lot of DRAM to hold the segment replicas. And the whole reason why we do this, we actually call this buffered logging. Is because we can't, or we don't really want to issue a write to disk for every single object that we write to RAMCloud. Yep.
So is the backup memory that you're running the same log DRAM that corresponds to the master? Is it the same memory or is it something else?
Question was, is this buffer memory in the DRAM of the backup the same memory as the master? These actually run as separate processes. So typically in RAMCloud, most of the servers will run a master. Well, actually, no, we've combined those into the same process now. It's in the same address space. They are different pieces of memory.
Is that maintained as a log as well?
Is this maintained in the log as well?
Is that maintained as a log structure as well?
These are just individual buffers. So the master has a giant chunk of memory that is divided up into pieces. Each of these pieces, not super important, but they're 8 megabytes. 8 megabytes happens to be a reasonable amount that we can, if you write 8 megabytes, the amount of time it takes to write the 8 megabytes compared to the amount of time it takes to seek to that location on disk is pretty large. So you can get, I think we calculated back of the envelope, something like 90% of the actual disk's like sequential I/O bandwidth. So the master maintains a whole bunch of these segments in memory for everything it's storing, and backups only maintain buffers for the segments that other masters are currently filling.
Do we do anything currently to prevent the slowdown when the logging is actually dumped to disk? So when the disk I/O is actually performed, do we do anything to prevent that slowdown?
Right. So the question is, what do we do when we flush a disk? I guess you're wondering, like, do we just block?
Yeah.
And there's one buffer here, and no. So there are actually multiple buffers. These are flushed to disk asynchronously. I think in the current code there's actually no limit, or typically there's a configurable limit, but I think it's set to more or less infinity at this point by default. That's for reasons of making kind of recovery faster. But yeah, so basically there are multiple buffers. They're asynchronously flushed to disk. Hopefully in the common case, there's always something available.
So question.
Yeah.
So at most, one of the backups can be on the same server as the master, and the rest of the backups are elsewhere in the cluster.
Good question. Where are the backups in relation to the master? I don't think we actually have the code implemented to discern where a backup is and to make sure that, for instance, a backup is not on the same physical machine or in the same rack or in the same cluster of racks or power failure domain or whatever. But I think there's...
Pretty much right, but
the one thing it does do is make sure it's not in the same process at least.
Okay. Question was, how accurate is that description? Answer is, sounds like it's pretty accurate, although there is logic that will keep a master from replicating to a backup basically in the same process. So on the same physical machine.
Because
Right.
you've already got a copy in DRAM.
Yeah. So does that mean that if I write a 100-byte object to RAMCloud, that 100-byte object goes into the master in some 8-megabyte segment?
Yep.
And that before that write returns on the client, that 100 bytes of data actually gets sent across the network again to a backup and then returns before the write return?
Yeah, so question was actually a good explanation of how this system works. Basically every time, this is taking me a little out of order. Okay, so basically what happens when a write comes into this system? So maybe I can backtrack a little. Yeah, the life of a write. So what happens when a master processes a write request? So basically, somewhere out of the ether, an RPC comes in from a client node saying, I want to write some key value pair. The master basically unpacks that RPC. There's a little bit of complexity. Let's assume that the key doesn't actually exist yet in the system. So it looks at the RPC, looks at the key. It doesn't actually exist. How does it know it exists or not? It checks the hash table, hashes the key, basically looks it up. There's no pointer there into the log. So then it wants to store this object. At any point in time, there is a head segment in the log, which is the segment that we're writing new data to. It's not full yet. All the other segments are either free, they're completely empty, or they contain data and we've already written them to backups in the past. So let's assume there's an empty head segment here. RPC comes in, writes it to the head segment. It issues RPCs to multiple backups, typically 3. Waits for the backups to reply. At that point, the backups actually have this piece of data buffered up in memory in the buffered versions of their head segments, of this master's head segment. At this point, the master assumes that the data is durable. You might be wondering, okay, that seems kind of weird. These are just sitting around in memory. How is their memory any more durable than this memory? We actually assume that we have some non-volatile memory, or we have a RAID controller with battery-backed RAM, and we can actually do a write to the disk that gets buffered up somewhere else in hardware that doesn't actually go to the disk. So we assume that that's volatile. Backups reply. Master inserts an entry in the hash table pointing from the key basically to that object. It's a little more complicated. The objects are actually scoped inside tables, but you can assume for now that there's only one table in the system. And then it can reply back to the client. So basically the steps are write into in-memory log, sync the changes to that head segment, and wait for the reply, and then insert the key into the hash table so that we can look this thing up quickly in the future, and then we can reply to the client. Okay. So there are
when the mix up comes, do you append it to the segments that have some empty space, or do you make a new segment?
Right, so I guess the question is, what happens when you run out of space in that head segment? Yeah. So for simplicity, objects are only ever written, so these key value pairs are only ever written to single segments. They're not allowed to span segments. So for instance, if this head segment fills up quite a bit, maybe up to here, and you want to write an object that's a little bit bigger than whatever the space is left, we will actually create a new segment to write that object. We will not write a little piece of it here and a little piece elsewhere. And the main reason for that is simplicity in the system. We don't want to have to add extra metadata so that we can deal with the fact that objects span multiple segments, especially because they will span different segments on different backups. That'll just complicate recovery a lot. So when you actually have to read these off of disk in the future, you might read a part of an object on one backup server and part of the object on the other, and then we'd have some massive shuffling where we'd have to stitch these guys back together.
So that means you could have like 50% wasted space if you were to constantly write objects that were exactly half plus 1 of 8 megabytes.
Right. So the question is, how much space do we waste here? We actually have a limit in RAMCloud. So our segments are 8 megabytes. We have an object limit. So segments are 8 megs. Objects have to be at most 1 megabyte. I can't remember if that's including the key or if that's just the data portion. But basically, objects are fairly small compared to segments. And the waste is not actually at most a megabyte. We'll get to that in a little bit. Yes?
Is this the right time to talk about segments? Or is it too detailed?
And I don't know whether I should go kind of depth first or breadth first in this.
Whatever you think.
There's a lot to dive into. I don't know, maybe I could turn this into a choose your own adventure.
I'd probably wait on segments for a little while. There's a little something to explain first.
Yeah. Well, I mean, there's a lot we can dive into. I mean, in terms of like hacking on the system and implementation wise, I've completely papered over like what the structure of segments are and what objects look like kind of internally. What bits do we actually store in these things? I could dive into that. It's
Later's fine.
later's fine.
Do your scheduled thing first.
We're like way off my scheduled thing anyway, so.
A broader question, if you
Yeah.
want to get that now or later. Suppose that we had a large persistent memory store that's slower than DRAM but still much faster than disk. How could we change this design to take advantage of it in terms of the backup writing?
So the question is, assume that we had some memory technology that is
That is
much
non-volatile,
non-volatile.
persistent, but about 10x slower than DRAM, but much faster than disk and much faster than SSD.
10x slower than DRAM. That's getting pretty close to SSD, but so assume we had some weird memory technology that is an order of magnitude slower than DRAM, non-volatile. How would we use it in this system? Is it cheaper?
Presumably, yes, it's cheaper than DRAM.
And what do you mean by slower? Do you mean bandwidth or latency?
Latency, like write latency. But not, I mean, assume bandwidth is about equivalent.
Then that's actually pretty good.
That'd be great.
If it was
If the latency is 10x worse, then presumably you could read an object in, I don't know, half a microsecond or so. That's actually not too bad. If we had that, we could probably keep the hash table in DRAM, maybe, so that lookup isn't very slow, and then the object itself could be kept in this memory. And our RPC times with InfiniBand are like 5 microseconds, and most of that is not in the RAMCloud software. I think it's approximately 1 microsecond or so in the code that we execute.
Currently measure 1.3.
Yeah.
Just server side alone. Is that considered part of RAMCloud?
That's end-to-end the server side.
Yeah, end-to-end server side. But that's not InfiniBand though, because that's already on the server endpoint. That's why I'm wondering where the cost is actually coming from. But I'm still digging into that.
You'll be able to tell us in a while.
Okay, let me try and like steer this kind of back into the order that I sort of expected. So, right, introduce RAMCloud, log structure. Why did we choose, right? So never really addressed, it makes sense, hopefully, to you why we chose to use a log structure to write this data onto backup disks, because the whole point of log structure is that we can write in very large IOs, and that's important for disks. So why do this in DRAM? That seems kind of a little bit weird. The initial reason, historically, so why log structure for DRAM? If you want sort of the slightly revisionist explanation, I'd tell you that we were brilliant, and this actually is a wonderful way of managing your memory for various particular reasons. The historical truth is that initially this was easy. And what do I mean by that? I mean that eventually the master has to do various things to manage the data stored on backup disks. So, for example, the log cannot grow unbounded. Eventually, some stuff is going to be deleted. Maybe there's some objects deleted here. That's just going to be dead data taking up space on disk. Eventually, we're going to have to defragment what's stored on disk and also what's stored in memory so that we can get some of that space back. If we let the logs grow too large, we'll just run out of disk space. And well before that, we're going to have very, very long logs, which means that it'll take a very long time to read those off of disk and process them if a master crashes and we have to recover the data that was storing. So in order to do this defragmentation, we have to know what's stored on the various backup disks, and the easiest way to do that is actually mirror the same structure. So if we have the same segment here as we have stored here, then we can iterate this thing in memory, know exactly what's stored there without ever having to go across the network, suck the thing off of disk, so on. So kind of the main motivation was it's very easy, especially to track log on disk. And this is important for basically, I'll get to cleaning in a moment. This is very important basically for getting free space back. Question? Yeah.
If people keep trying to write to RAMCloud after it's already full, what will RAMCloud actually do? Like if the RAM memory is completely full and we can't actually write, will RAMCloud throw an error or will it block?
It will.
Repeat the question.
Yeah. Question was, what does RAMCloud do when we run out of memory? It does not return an error. The client will block. The client will block.
The client will block. I see.
Yeah.
We try over and over.
The point is we don't want the client to have to deal with every possible error case, basically, including that you've filled up your storage system. So the client will just keep retrying. In fact, not super important, but the way we actually do that is masters will just say, sorry. An RPC will come in, client will say, I want to write this thing. The master says, sorry, dude, try again. I can't service it right now. I think we use that kind of commonly in the system to deal with error cases in general. Just send a status, I'm not ready yet, and kind of leave retrying to somebody else.
So the RPC does return. It just
Completely
says,
hidden from the client.
what you mean, like if I instantiate the RAMCloud client and I make this RPC call, so that call would just never return, basically, it would just block.
From the perspective of your application, underneath the hood, the actual library will be retransmitting the message over and over again.
I see.
So question was, what is the client who's actually using kind of the high-level write API see? He sees his function function call take a very long time, and somewhere underneath that there's some logic that deals with the fact that a server might say, you got to try again.
We hypothesized, probably is going to be on the video, we hypothesized that this retry is actually a really, really important thing in the system. We didn't have it initially. We gradually started adding it in and come to appreciate it. The problem is that if you need to wait for something, you don't want to be waiting on the server because you're consuming resources that might actually be needed to finish doing the work that you're waiting for. And so you get this terrible congestion if you have thousands of RPCs piling up on a server all waiting for something. So instead, we go back to the client and do the waiting back on the client side, where we're not holding any server state, and then retry again from the client side. It's just a very convenient way of dealing with all sorts of situations. Actually, in some situations, when you retry, you're actually going to have to retry to a different server. If a server crashes, for example, its objects will get reinstantiated on a different server. And so you actually, when you do the retry, you may end up talking to a different server than you did the first time around.
So John made a point that this is basically a very simple way of handling a lot of failure cases. Basically, we don't want to inundate a server when it's kind of in a bad state. So it's better just to say, I can't deal with this now.
And some of the motivation there, I would say, at least for some of us at the time we started RAMCloud, we had a hunch that this was a better storage allocation mechanism than malloc, although the proof didn't come until many years later.
Right. Yeah. So.
Well, not all of us believe that at the time. It's a controversial hunch.
Right. So it's 1 minute. So it's if you're John and if you're me, I don't actually remember, but we had some hunch that this might not be a horrible idea for other reasons. That maybe managing memory in this way might make sense. One reason to believe this is that I think there are like 1,500 or 2,000 like garbage collection memory management papers in existence. Like this is not a field that has reached any kind of stopping point or conclusion. So people keep trying to make better memory managers. Question?
Okay, so you said that the main thing that you have this logic structure is that like it's easy to reply to log and go and find the segments and come back, right? But the different segments are on different backups, right?
Mm-hmm.
You don't put the whole log on, for example, 3D application. How do you manage this? There are different segments and different.
Yep. Great question. Question is, your master has been storing a bunch of data in segments. It's been replicating them to different sets of backups. Kind of in the limit, you might have a piece of your log on every backup in the cluster. How do you manage that? How do you, when you have to replay the log, how do you get all that junk back together and so that you can actually replay the data?
Can you suggest deferring questions that are on totally different topics so we don't just completely go off the wilderness?
It's not a completely different topic. I mean, at some point I'd like to kind of dive into the structure of these segments, which would include log digests, which is the way we do it. So maybe I can just answer very briefly. Each segment actually contains a list of all the other segments in the system that are part of the log at that time. Then basically all we have to do, is a little bit more complicated than I might make it sound, but all we have to do is find the head segment that contains the most up-to-date list of all the other segments, and then we know what the IDs of the segments are, and then we basically talk to every single backup. We have to talk to every single backup to find the head anyway because we don't know where it is. We don't store it centrally because we don't want to have this central bottleneck where we have to every machine would have to tell where every segment it stores is. So we talk to every backup, we find the head segment, we know what segments every other backup has, and then we can kind of collate that information and figure out, first of all, do we have the whole log? Hopefully we do, and if we do, where it's all located so that we can read it back. Okay. So I guess it's probably reasonable to go into cleaning at this point. So kind of one of the most important aspects of log structured memory in RAMCloud is basically dealing with the fact that after a while, you kind of end up with this Swiss cheese log. You get some writes, you fill in your log segments with objects. You might overwrite some of those objects. So in RAMCloud, we always store objects in a copy on write fashion. So you write a new version of an object, you update it. We don't actually update it in place. We write it to the end of the log again. So you end up with older objects taking up space in the log that you don't need anymore. You might delete objects, in which case you get the same thing. So eventually, this append-only log that we have fills up. And if it fills up with live data, then, well, there's nothing you can do. That's fine. But if it fills up with a bunch of old cruft that's just taking up space, then that's a problem. Then we want to get that space back so we can store more data. And so the way we handle this is with a technique borrowed from LFS. It's called cleaning. And it's basically just a way of defragmenting your segments to get free space out. It's kind of quite similar to copying garbage collectors that are used in many programming languages like Java. And so I'll kind of go historically again. So what does cleaning do? So originally RAMCloud, we'll make this somewhat more complicated, but originally RAMCloud basically looked exactly like this. We had segments in memory and carbon copies of them exactly on backups. And what cleaning would do is it would free memory and disk space simultaneously. So in each RAMCloud master, there's an entity called the log cleaner. When you start running low on memory, or there are a few other triggers, but for simplicity, when you start running low on memory, the log cleaner kicks in and it says, okay, I need to defragment segments. I need to get free space back. So cleaning basically is a pretty simple three-step process. The cleaner first selects a bunch of segments that it wants to clean. It then writes all the live data from these segments to new segments that we call survivors. And then it can free the old segments that were cleaned. And these can be reused by the system. So, for instance, correct, yeah. So it will free the old segments both in memory and on backup disks. And so, for example, this process might look like maybe you have a handful of old segments sitting around. We'll use 2 just for simplicity. Maybe they're kind of Swiss cheese here. So this is free space that's occupied by deleted objects or equivalently overwritten objects. So you might choose these 2 segments to clean, and basically what happens is you write them out into hopefully fewer segments. And so you've gone from 2 segments with a lot of fragmentation. You can free these guys. You can basically dump all the data that's in them and reuse them for new head segments when you want to write more data. And you've kind of coalesced all of their live objects into a smaller number of segments.
So the bunch of segments that you choose don't necessarily need to be co-located. Don't need to be adjacent.
In memory, no.
In memory, in DRAM. So you can just choose like any set of segments to clean where they are.
Yeah, so question is, do these segments have to be contiguous in memory? Do they have to be near each other? No, it doesn't matter. They can be any segment in the system. I mean, if you have a 64 gigabyte server and 8 megabyte segments, you'll have about 8,000 of them. So you have a lot of choice. I guess that brings up the question, how do you choose what segments to clean?
And also on this, that you would be cleaning just like parts of the log that are like not necessarily contiguous.
Correct. So when we clean, we're not cleaning contiguous pieces of the log.
Right.
I mean, beyond what's contiguous in that 8 megabyte chunk.
Yeah. I viewed like the log as the log is just sort of like always writing to this head of this log, and like you're cleaning parts of that log that are sort of like behind that head point, and you're creating all these holes in it. How do you go back and like fill those holes? Use that space that's been freed within that space that's freed.
Contiguous even when you're writing.
Even when you're writing to the log, it's not just writing to the next memory address plus 1.
No, no.
Only
No.
within a segment.
Only within a segment. I see. So then the disks also have a hash table that's telling you no.
Disks have no hash table, no. What are you wondering? What would they?
Just that like
that
when you
for?
want to reconstruct this hash table and the master's memory, I
Correct.
assume that what you would do is you would start at the very tail of this log, and you would run all the way up to the front of the log, and then you would, as you go through this log, you would just recreate the hash table along with all the data in DRAM.
That's basically true except for the ordering.
Yeah, so the ordering would be strange, right? Because if you have an updated element earlier in the log, then
Well, that's fine.
an old object later in the log, you must need to know that. You need to know that somehow. And evidently, it's not based on the position in memory. It must be based on a timestamp.
Okay. Yeah, okay.
Tombstones, right?
Version numbers and tombstones,
Oh,
yeah.
it's based, okay, I see.
Should I dive into this?
Your choice. I understand it now.
Let's leave that off a little bit. I mean, I'd like to get to kind of the structure of what the objects actually contain, and get into tombstones because they're important and a pain. But I think I'll leave that off for a minute. I don't
You
think.
just give a couple of sentences on each of those steps, like how do you decide which segments are the best segments? How do you decide
Yep.
which object are alive?
Yeah. So let's drill down into these a little bit. How do we select which segments to clean? We use a cost-benefit approach. Similar to LFS, although if I'm not wrong, I think Mendel had a better approach that he implemented in a simulator and didn't report in his paper. Though I might be completely wrong about that. But that's what's in my dissertation in any event. We use a cost-benefit approach, and basically you might say, well, it seems to me that the best segments to clean are the ones with the smallest amount of live space in them, because the cost to clean a segment is proportional to the amount of free space. Or the amount of live data. So, and the cost grows pretty obnoxiously. So, for instance, if you have 50% of a segment is live, then you have to end up having to copy 50%, and not just copy 50% of the live data in memory. You have to write that to You have to send that over the network 3 ways to backups. Those have to write it to disk. So I/O is pretty expensive, and we'll get to tricks for dealing with that in a little bit. You have to copy 50% to get 50% back. And if your segments happen to have very little free space in them, maybe most of your data is actually alive in memory, then if you copy 90% to get 10% back, well, that's a significantly worse ratio, and it just you end up with the cost of cleaning kind of goes like this, where this is the utilization of the segments, how much space is actually consumed by live objects. So the cost basically goes through the roof. You approach 99%. You're basically copying 99 units for every unit of space you actually get back. So it's extremely inefficient.
In some papers, people use the phrase write amplification to refer to this. That for each byte of new data you write, you actually have to do many more bytes of I/O. So for example, at 90% utilization, the write amplification is a factor of 10. For each byte of new data, you're writing 9 bytes of old data as part of the cleaning process to free that space. And so you're doing 10 times as much work as you might think from just the data alone.
Yeah. So John brought up there's, I guess in the early 90s when they came up with this, they defined a term called write cost, where they basically said, if you're cleaning all the time to generate more space for you to write new data to, then you're not just paying the cost of writing that new data, you're paying the cost of copying other bits of live data to get that space back. So that the sum of those is basically your actual write cost. And nowadays, I think a more popular term is write amplification, which is used much more in the context of SSDs, which kind of under the hood use something analogous to a log structured file system because they have to move data around because they can't actually update in place. So we use a cost-benefit approach, and this actually takes into account 2 things. So you might say, okay, so the cost is proportional to the amount of free space. Why don't I just greedily choose the segments that have the least amount of free space? Mendel has an entire dissertation chapter on why this is not the best idea. And it turns out that if you take into account not just the amount of free space, but also I kind of like to call it the stability of the data in the segment, then you can actually do a lot better. So it turns out that sometimes it's better to clean a segment at higher utilization when its data is not going to be overwritten very soon in the future, because that allows you to wait a little bit longer for other segments that have much hotter data that will hopefully expire soon, and you can actually get a net win that way. So you can wait kind of for the segments that are going to decay quickly to decay more and more and more, and then they're cheap to clean. Let's dive into step 2. So that's how we choose our segments to clean. How do we know that data is live? That's pretty easy to answer, but it will introduce another concept here. So for objects, this is very easy. Objects are alive if and only if the hash table points to them.
So you scan another hash table, find the objects pointing to that segment?
So John suggested a wonderful idea of scanning the entire hash table to figure out which objects in a segment are alive. No, we do it somewhat more intelligently. We scan the segment and check the hash table.
That then implies that the segment is relatively self-describing.
Yes, we can jump into that detail. Yeah. Yeah, so maybe it's a good time to segue a little bit into that. I haven't introduced Tombstones yet. I don't want to go down a rat hole. There are other objects, there are other pieces of data in the log that describe what objects are dead. These are called tombstones. So every time you delete an object, you write a tombstone, because we can't go back and like scribble out the object that's stored in the log. That would require, you know, an expensive seek. I think it would open up a whole bunch of consistency issues. What happens if you scribble it out in one backup and not another, and you end up replaying the log from the backup that you didn't scribble it out on, things like that. So every time we delete an object, we write a tombstone. Every time we overwrite an object, we write a tombstone and the new object. So for every dead object in the log, there exists a tombstone corresponding to it. And we use that during crash recovery basically to have them self-annihilate. So, you know, if we see an object, we will not recover it if it also has a corresponding tombstone in the log.
Tombstones will also have version numbers.
Tombstones will have version numbers, yeah. Yeah.
And tombstone can either prevent the replay of a particular object, or it could undo the replay of a particular object, depending on which order they're seen in.
Yeah. So yeah. So. All right. No. Let me do that. This is hard to kind of linearize, but yeah. So let me. Somebody hold on to that stack pointer for me. We'll get back to it eventually. So it's probably worth talking a little bit about what do these objects look like? What are we actually writing into the log? So everything that's written to the log is called an entry. And so if this is an empty segment that we're writing something to, let's say we're writing a new object to this segment. Before writing the object, we actually write an entry header that describes what we're writing, and then we'll kind of write the object itself, which is a little bit more complicated than just writing the object itself. The entry header contains two fields. There's a type field and there's a length field, so that we know what this thing is. Is it an object? Is it a tombstone? Is it a log digest, which I'll get to? Is it something else entirely? And the length just describes how long the thing is in the log, so that they don't have to contain their own lengths. Just so it doesn't really confuse people when you're looking at the code, the entry header is actually, I guess I kind of lied a little bit. The entry header is actually variably sized. So the first byte of the header tells you the type and how many bytes we need to store the length. And then bytes 2 through 5 actually contain the length itself. And the whole reason this was done was just to ensure that we had, I'm sure you can come up with more clever ways for very small objects, but basically we wanted to use the minimum amount of space. So if we have a really small object in the log, we want to have the smallest amount of metadata for it. Okay, so if we're storing an object here, we'll write an entry header first. And the entry header basically allows us to iterate the segment very easily. So you start at the front. The first thing should be an entry header. It tells you what the type is, the length is, and then you can jump to the next entry header and so on. If this is an object, then we actually have, use another color here. This is an object. It actually consists of a fixed object header And then there's a variably length key and value following it. The key and the value are just uninterpreted blobs of bytes. The object header contains a bunch of information. So there's a 64-bit table ID. I haven't really talked about tables. There's not a whole lot to talk about in the context of this. But basically, a table is a namespace for keys so that we can have the same named key in different applications or whatever. There's a 16-bit key length. So we know how long this is and where the beginning of the value starts. There's a 64-bit version number. And this allows us to differentiate between different versions of the same object in the log. So when we replay, we will take the object with the highest version, assuming that it doesn't have a tombstone that indicates that it's been deleted. What else do we have in this thing? I see. And there are a couple of other fields. There's a 32-bit checksum, so we can check the integrity of an object when we replay it. It's part of the object itself because of the way we implement crash recovery. And we have a 32-bit timestamp, which records, it's kind of like a Unix timestamp. It's a second granularity timestamp of when the object was created. Might actually be useful in the future for clients to use this, but the reason this exists for now is for cleaning. So that when we choose some segments to clean, we don't just write out objects in whatever random order. We actually sort them by their age first, and then write them out. And the assumption is that if we do that, we can segregate objects based on how old they are and hopefully based on how long it will be until they're deleted in the future. So the older an object is, the higher the probability that it will survive for longer. And then you can create kind of sets of hot segments and cold segments. The cold ones will basically have a lot of data that doesn't decay quickly. Hopefully you won't have to clean them very soon in the future. And the hot segments hopefully will decay very, very quickly and they'll be very cheap to clean. So that's just a minor, well, I guess it's an important optimization for cleaning. Right, so this describes, so we described how objects are stored in segments. Let's say we deleted this object for some reason, then we'd create a tombstone. Yeah.
The cleaner it doesn't do it one segment at a time cleaning. It takes a bunch of segments and then looks at the ages of all the different pairs in that whole set of segments, and then is able to take the oldest ones and all kind of like batch them together into a new segment, and take the hot ones and put them in another segment themselves to try and achieve this sort of age optimizing feature.
Yeah, so the question was, and the question explained basically exactly how this works. What does a cleaner do, with, more precisely, I guess, what does a cleaner do with these ages? Yeah, it looks at every single object in the set of segments that it chooses to clean. It actually does a sort just on the age of these things, and then it writes them out by, I don't remember, but I don't think it really matters too much. It, oldest or newest, and then writes those, writes them in age order to survivor segments, and then you hopefully end up with a nice separation of hot and cold objects. Okay, so what's the format of the tombstones in the log? So tombstone has an entry header like everything else that's written in there. There's a tombstone header, and then there's a key. So there's no value because we're not actually storing the contents of an object. What does a tombstone header look like? It's pretty similar to an object header. There's a 64-bit table ID. So this in combination with the key uniquely This in combination with the version and the key uniquely identify the object that was deleted. The other important thing is there is a segment ID.
Key length also, right?
Yeah, there's a key length in here. Actually, we don't need the key length, but I think we have it in there. That's kind of weird. Because, yeah, I mean, we could calculate the key length because this is a fixed size, and we have the length of the total thing here. So we should probably get rid of that. There are a few other things. I think they have timestamps as well, though it's not really clear to me exactly if those are as beneficial for objects as for tombstones. And checksums for integrity. Probably the most important thing, the most important new thing here is the segment ID. What is this and why do we have it? So every segment in the log, every segment for a particular, let's try again. Every master, as it's allocating segments, assigns them a unique ID. The IDs are unique to that master. They're not globally unique. And it's basically just a counter that we increment. So every time we create a new head segment or every time we create a survivor segment, we increment a counter and that segment is given a particular ID. So why does a tombstone have a segment ID in it? Well, it's pretty easy to figure out when we can delete an object or when we can get rid of an object during cleaning. We just check the hash table. If it doesn't point to it, it can't be the most recent object. We can just ditch it. But what happens when we look at a tombstone? How do we know whether we need to keep this thing around or not? Well, so there's a very simple requirement that we have, and that's just that if there is an object that has been deleted that's in the log somewhere on disk, then we have to have a tombstone for that. It has to be present as well. Otherwise, that object could potentially come back to life when we replay because we won't see the corresponding tombstone for it. And so we need to be able to keep around the tombstone as long as the object is around. What's a really easy way to know whether the object's around or not? Well, if the segment that the object was last in when it was deleted happens to still be in the system, then the object is still in the system, and we need the tombstone. If the segment has been deleted, then that means the object is not in the log anymore. There's no way we can replay that during recovery, and we don't need that tombstone anymore. Does that make sense?
So does the recovery master keep a length of all, not the recovery master, sorry, does a master keep a list of all the segments in use?
Yeah. So question is basically, how do we go from a segment ID to knowing whether or not that segment still exists? There's a hash table. So for every one of the 8,000 or so segments, there's an entry in there that says, it still exists. That's all.
And why do you need the timestamp here?
Um,
You have the version.
Well, I mean, so the question is, why do we have a timestamp here? But why do we have a version 2? I mean, the version isn't really, in the version, I guess it is some sort of timestamp, but versions can kind of jump around in weird ways during recovery.
Is the timestamp used on all of them?
The timestamp is used in the exact same way that it's used with processing objects by the cleaner. So we sort tombstones by age, in the same way we sort objects. Not entirely clear to me that that's particularly important. Haven't really tried to see what happens if we just get rid of it or something like that. I mean, the thing is, if you have a lot of live data in your server, then it's going to be relatively expensive to clean it because you have to copy a lot of stuff to get a little bit of data back. And if you have a lot of live data, that means you don't have a lot of space that you can actually store tombstones in. So that means you have relatively few tombstones. And it probably doesn't matter too much if they're ordered in any great way. So my gut feeling is that it's probably not particularly important, but don't know. Don't know how the system would behave if we just got rid of the timestamps and ordered tombstones when we write them out during cleaning in any arbitrary way. Okay.
Would it be reasonable to assume that tombstones are going to go away relatively soon? Does it seem more likely that a tombstone will get deleted than most objects?
Is it more likely that a tombstone would be deleted than most?
Because we know the object that it
Objects.
corresponds to has been deleted. And so it's just a matter of when the cleaner gets around to cleaning that segment. I'm wondering if it makes sense to sort tombstones as if they're the youngest objects in the system.
I see. Question is whether we should sort tombstones as if they're the youngest. I imagine that most of the time that would probably work out, because most of your deletes, if you are segregating data into hot and cold, then most of your deleted objects should be concentrated in a few segments that you will likely clean in the future. That won't necessarily work all the time. You might delete an object in a very cold segment. It might be a very long time until you process that. So putting its corresponding tombstone in a hot segment might not be the best idea, because you might end up having to copy it multiple times.
I guess the timestamp mechanism effectively does that. The timestamp reflects when you created the tombstone, when you deleted the object. So initially the tombstones are the youngest things in the system.
Right.
If they live a long time, then maybe that's a sign that they continue to live a long time.
Right, yeah. So point was, by basically using the timestamp in the same way as objects, you treat them the same. If the tombstone has been sticking around a while, then you kind of stuff it in a cold segment, because that means that probably its object is in a cold segment. That segment hasn't been cleaned, so that object is still sitting around. So yeah, probably not a completely unreasonable feature of the system. Any questions on this stuff?
Question from a little back. So I didn't understand when the tombstones are generated. I mean, when is it that you go see this object is not anymore alive, and then you generate a tombstone there?
Yeah, good question. Question is, when do we write tombstones? And the answer is that if we're deleting an object, let's say we're here in the log, we get a delete RPC that comes in. Oops. Says I want to delete this particular object. Then it's basically like a write. We write a tombstone into the log for that object. We replicate it to backups in the exact same way. We reply to the client when that's been written. If instead of deleting an object, we're actually writing the same object, yep. So if we're overwriting an object that's already stored, it's already alive, there's an entry in the hash table, basically what happens is an RPC comes in, the master sees that it's a write, it first checks in the hash table to see if that object exists. If it does, it says, oh, okay, I'm overwriting something, so I need to generate a tombstone for this. And then basically it writes a tombstone and the new version of the object. So tombstone referring to the old version and a new version of the object in the same segment.
What if the tombstone fits in your head segment, but there's not enough room for the new version of the object? Is it okay to put the tombstone in one segment and the new version of the object in a separate segment?
Yeah, good question. What happens if you're here and you don't have enough space for both, but you decide to store the tombstone by itself, and presumably the object in the next segment is that cool? No, not a very good idea. Problem is, you could run into the situation where you've written the tombstone, you've sent it off to backups, you haven't allocated the next segment and written the object into it, or maybe you have, but it hasn't been replicated to the backups yet. Server crashes, and this looks like it's the head of your log. You replay this, and the latest piece of data for that particular object happens to be the tombstone, and you lose it. You don't have the new version, but you have a tombstone present. So what we want to ensure is that we have basically a way to atomically write both of these things, because it would really suck if you lost data. So there are kind of two components to that. One is a very simple rule that we always write both into the same segment. We're basically guaranteed that we can fit it because our objects are much smaller than our segment size. So that's not a problem. If we happen to run out of space, then we say, all right, we're done with this segment. We'll create a new one. It's the same thing that happens if we have objects that are too large to fit at the end. And then we need some way to ensure that both of these are kind of atomically written to the segments on backups, because it would really suck if we wrote them together right here, but then somewhere further down in the system, the backup says, oh, okay, I'll write the tombstone, and it doesn't write the object yet. The way we do that is, I guess I can introduce something new. I mean, one way to do that is to basically ensure that there's a single operation that syncs both of these at the same time, and that's actually what happens in the code. We actually append multiple things to the log, and they're not actually made durable until we call a sync method on the log module, which ensures that everything is kind of blasted out to the log at the same time. And furthermore, to ensure that this can happen, I mean, you could say, okay, we'll mandate that every write to backups uses one RPC, so it's atomic. But I think for various reasons, we don't really want to have that requirement. We'd rather not to have this dependency between layers, and for the part of the system that handles all the replication, that it can kind of break things up in whatever way is convenient for it. So we actually have this kind of cool piece of metadata called a certificate. So every single segment has a certificate. And basically, all a certificate is a length, and that's all we really need for this behavior that we want. It also has a checksum. So what happens is the master will write the tombstone and the object into the segment. It will call sync. Sync will say to the backup, okay, I want you to write this stuff, and when you have written all of it, I want you to apply this new certificate. I want you to store both the segment in memory and eventually on disk. And I want you to keep around the latest certificate that contains the latest length of this thing. So basically, you know, if the system wanted to, it could actually write the tombstone first, or it could write part of the tombstone, or part of the tombstone and part of the new object. Doesn't really matter. But the initial certificate, maybe certificate I or whatever, will only point to this point in the log. Until it has written everything that it wants to, and then the master basically with the last RPC that it sends to the backup will say, okay, here's the new certificate I+1, and suddenly everything that was appended before is kind of atomically brought up to that point. Does that make any sense?
Is certificate only transitory mechanism, or does it actually get written to the log itself?
It has to be written to the log.
So are you going to stack up certificates then, or are you going to delete previous certificates?
You only need the last certificate.
It's actually
Yeah.
stored on the side. Next to the segment.
One per segment.
Yep. So question was, do we keep multiple certificates around? We just need the latest one per segment. Yeah.
Just ensures that the segment stops at well-defined points. The segment can't end partway through an interesting atomic update.
Yeah. Yeah. It's basically like a kind of a commit record off to the side.
That too, like Steve was hinting at, is that now you can use any means necessary or any number of RPCs you want. All of that's orthogonal so you can replicate it any way you want to. The data can get there in any order, and you can get there in any length or whatever, as long as it uses kind of this. Once it's all there, you move atomically from one certificate to the other. It will still appear atomic to the recovery mechanism. So.
Yeah.
So it kind of uses a lot of flexibility in how we implement that.
So Ryan's just stressing the flexibility that not only can we write whatever we want kind of in order, you can write out of order, do whatever, doesn't matter. The certificate is just a nice way of kind of atomically committing all that crap once it's been in there. So I don't think we actually ever write anything out of order, but you could do it.
I'm going to show a much floppier mechanism for replication next week. And
Okay.
The whole point is that this makes it easy.
Okay.
Should we stop and do a time check? So first of all, where are we in terms of all the material we prepare? I'm guessing we're going to want to do another week of log structured memory next week.
We're not too bad. I mean, I guess the big topic left over is memory compaction and seglets and how that kind of makes this all a little bit more complicated. And then I would like to go over kind of all the classes that are involved.
And how are people doing? Who's feeling energetic and would like to go on a while longer today, as opposed to calling it quits today and resuming next week?
I'd be happy.
Nobody's raising their hand, so I'm thinking maybe we should wait and continue next week.
Okay.
A lot of very good material, but like if you send more in, then you might not get the process fast enough.
That's what the video's for. You can get the play-by-play on the video.
That is true, but it's harder to generate questions on the fly when you're not processing information fast enough.
That's true. Okay.
I'd rather to watch the video and then go ahead and think about these things, and then next week I can ask more questions about things.
So it sounds like you think you're near the end, but I'm guessing that you'll have lots of questions. I'm guessing we can probably spend next week finishing this up. So only plan on doing this
Sure.
the segment replication in 2 weeks.
Okay.
Okay.
Until next time when I magically show up with a new shirt.